of a random variable x is expectation of x minus e of x, that means mu x. How we can write? Very simple, like earlier, minus infinity x minus mu x to the power n fx of x dx, right? Now you see, when you do mu x, so DC part is the mu x, the DC part, that means this a, and if we subtract it, this only noise part will remain, and the moments will give more important or can characterize the noise. Mu x is the first moment, the random variable with the first moment, and then we keep on getting the moments. So for discrete random variable, parallelly we are discussing. For discrete random variable, why parallelly we are discussing? Because discrete random variable is very important for our research, because we need to incorporate computer everywhere. So for discrete random variable, we can write expectation of x minus mu x to the power n will be equals to summation over k xk minus mu x to the power n xk. Okay, so this is what we need to do. So in central moments, the mean is subtracted from the variable. Like the earlier we said, the mean is subtracted from the variable. It will be useful. So there are name. So the first central moment, zeroth central moment is always 1. We know the first central moment will be what it will be. So the first central moment very simple, e of x minus mu x, that will be e of x minus e of mu x, that will be mu x minus mu x will be equals to 0. Zeroth central moment will always 1, no need to discuss. So if we consider the central moment, first central moment and zeroth central moment plays no role. Central moment plays no role. These two has no role. Why these two has no role? Is always fixed. Zeroth central moment is always, and first central moment will always be 0. So these two are fixed, play any role. Which one will play role? The role, first thing, the variance or the second central moment will play role. What is so moment, then come to second central moment. How we call it second central moment? It is e of x square. You think this x is our random variable in one dimension. That's what happily we are writing square. But very soon we'll move to a area where the random variables are not a single dimension, or it is not a scalar. So it is a multi-dimension. So this square does not make any sense, because x become matrix. We need to write x minus mu x into x minus mu x transpose. That will come very soon. But we are in a simple scalar, all x random variable are scalar, so happily we could write the square. So this is the second, call it as a variance. So what is the variance? Sigma x is the variance. This will be equals to e of x minus mu x square. So this is called variance. And sigma is called standard deviation. Okay, so this will be equals to e of x square minus 2 mu x into x plus mu x square. This will be equals to e of x square minus 2 mu x into e of x plus e of mu x square, that is simple. So this will be equals to e of x square minus 2 mu x square minus mu x square, sorry, plus, so it will be e of x square minus mu x square. So this variance plays a very important role. Always we call variance of standard deviation is the second central moment, and it shows that how much your data is spreaded. This is kind of thing. So tell me, is it fine to all of you? This central moment, how the concept is coming, and why the second central moment is important, not the zero or first, and we can go for any central moment. That is not much issue. Okay. Tell, is it fine?
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So now, example, we calculate the binomial random variable mean and first moment. Okay, so for a binomial random variable, Ramsa, is it fine? Are you there?
Yes, sir.
Okay.
Yes, sir.
For random variable, yes, thank you. E of x will be equals to np, we know, and e of x squared, we know, that's what we wrote. Okay, next line, let's write e of x squared will be equals to n square p square, we have seen, plus np into 1 minus p. So can you tell me what will be the variance? Very quick.
NP 1 minus P.
Yes. So how do we get? Very simple. E of x square is, so sigma x square will be equals to n square p square plus np into 1 minus p minus n square p square, right? These two will cancel. It will be np into 1 minus p. That is sigma x square, right? Okay. So now similarly, can you tell? Oh, sorry. It is going to be expensive. Similar example, can you tell what will be the sigma x square for a random variable of uniform distribution of 0 to x to a? What will be? Tell me.
A square by 12.
It's very simple. So I am trying to write it. Sigma x square will be equals to e of, we can go way, earlier we have done e of x square minus mu x square. We could write 0 to a 2 square, then fx is 1 by a dx, right? So you calculate, you will get a square by 12. Komal, you are new, so today you could follow, right? Or is there any problem? Komal, she is not here. What happened? Komal, are you here? Need to add maybe. Add. Anybody is not here? Jafar is here. Ramsai is here. Satipriya, you are here. Then anybody is. Shreya also is here. Midul, Asna. Asna, are you here?
Yes, sir.
Asna. Okay, fine. So maybe only Komal is not here. She's dropped some. Okay. So some message came. Recording. Recording. Shreya, you are recording, right?
Yes, sir.
Shreya, are you recording?
Yes,
Okay,
sir.
fine. Okay, fine. So now let's keep on continuing. So this problem is fine for everybody, right? So now let's proceed further. So we are saying that standard deviation we define as some x equals to square root of e of x minus mu x square. Okay. So again, I am saying this square we are giving because it is single dimension. It's scalar. We will come to matrix notation very soon. Now there are two more things. How this third order central moment is important. Central moment we can say as it is e of x minus cube, and we define the coefficient skewness as the CS, that e of x minus mu x cube divided by sigma x cube. So this is called the skewness. Okay, there is fourth moment that is also important. Some problem is happening. Just bear with me. So fourth central moment, that is e of x minus mu x to the power 4, and that can we relate with the kurtosis. So coefficient of kurtosis CS, that is e of x minus mu x power 4 by sigma to the power 4. Okay, so now can anybody skewness or the kurtosis? So let's first tell me what is the physically. It can be negative. If it is positive, how the PDF density function will look like. If it is negative, look like. If it is 0, how it is look like. Can anybody can tell me? Anybody? You must know. Jafar, any idea?
Sir, kurtosis, and that gives like how concentrated is. Sorry, sir.
you tell?
I'm not like hearing you.
Okay,
Hello?
fine. So no problem. So skewness can be 0. If skewness is 0, that means the PDF is fully symmetrical. So skewness equals to 0 means the PDF is symmetrical. Mean. So if we say that we have a Gaussian distribution like this, where this is the mean, so what will be the Gaussian distribution? That is, for a Gaussian distribution, we know that it is a symmetrical around mean, so the skewness or CS will be equals to 0, right? Now, what is the meaning of positive and negative? So CS is positive. It means to the right of its mean. It is if is skewed to the right of its mean. Skewed means long tail. Okay, long tail, right of its mean. So if I draw some distribution like this, that means it is skewed to the right of its mean. Okay, that means it is positive. Negative is just opposite. It is negative. It means that PDF is skewed to the left of its mean. Okay, this is the physical interpretation. Negative skewed to the left of its mean. Positive means its kurtosis. If it is more, that means PDF is concentrated near its mean, and if it is less, that means PDF is not concentrated. So random variable which has the large coefficient of kurtosis will have a larger peak near the mean. Okay, so let's write kurtosis. Kurtosis CK, if it is more, the PDF is more concentrated, PDF is more concentrated over the near the mean, not over, near the mean. If it is less means PDF is less concentrated. More concentrated means what? Means large peak. Okay, large peak. Less concentrated, that means it has a less peak over the mean. That's what its physical interpretation is. So now what we learn? We learn the central moment. We learn the central moment of order 0 has no meaning because it is 1. Central moment of order 1 also has no meaning because it is always 1. Always 0. Central moment of order 2 has a meaning, and its physical interpretation is variance. More it is, the PDF is more spreaded. Less it is, the PDF is less spreaded. Kurtosis, which is proportional to the third order moment. So it says if the PDF is skewed or not. If the PDF is skewed, the kurtosis will not be 0. If it means PDF is not skewed, it is symmetrical. Kurtosis is positive, that means it's skewed over the right hand side of the mean. That means it is a long tail you can expect on the right hand side. If it is negative, that means left hand side you can expect long tail, that is the skewed. coefficient of skewness, and then kurtosis, coefficient of kurtosis. If it is more, you expect that peak, heavy peak near the mean. If it is less, you expect that peak will be less. This is all. Tell me any query. Call is still not here, I guess. Are you in call? Okay, most probably no. Kirti, are you in call? Kirti, today she is absent. Okay, fine, she is not online. Komal, you are also not online?
Sir, I am.
Okay, you are online. Fine. So is it okay? So I was asking to you because today is your first day. So is it fine? You are following?
Yes, sir. Yes, sir.
Okay, fine. All of you tell me if any query or if it is fine to all of you, then we can proceed.
Yes, sir.
Yes. Yes, sir.
Okay, fine. Okay. Okay, so then now let's do an example, which is simple example. So an exponential distribution PDF of an exponential distribution is given by fx of small x will be equals to b e to the power minus bx ux. Okay, b e to the power minus bx ux. So we know the mean, or mean is given. I don't want you to calculate mean. 1 by b. What will be the nth central moment? So nth central moment. Can you calculate? What will be the nth central moment? Quickly. Or shall I do it? Okay, let's do it. Solution. E of x minus mu x to the power n will be equals to ux means 0 to infinity, it will come. Then x minus 1 by b, x minus mu x to the power n, then fx b e to the power minus bx, ux we don't write because limit we are taking, dx. This will be equals to b will come out b by need to do some transformation. Let's y equals to x minus 1 by b, substitution. So this will be y to the power n, then y0 means x0 means y equals to minus 1 by b, infinity means infinity, then b means x minus y, 1 by x minus y. How do we integrate this? Any help from anybody? E to the power minus bx. Okay, x 1 by b equals to x.
So we can proceed the same way. Then
Yes.
we can put the value of minus bx that we can calculate
Yes.
from this y is equal to x minus 1 maybe. So that will come out to
Yes.
be
So bx will
minus
be
1. That will
minus
come out to be minus 1 minus by.
minus 1. Minus by. Correct.
So this we can take out e
Out.
raised to the minus 1.
Yes. dy. Yes. So b by e to the power 1 minus 1 by b to infinity y to the power n e to the power minus by, right? Minus by right? B y to the power minus by dy. So this we could write 1 by b to the power n summation n equals to 0 n by factorial n minus 1 to the power n. Okay. So if this is so, now tell me what will be sigma x square or variance. Quickly calculate and tell me from here. N is 2, right? So quickly calculate. So if it is 2, 1 by b square summation m is 0 to 2 factorial 2 by factorial m minus 1 to the power n. So this will come as 1 by b square. Okay. Now you calculate the coefficient of kurtosis, skewness first, e of x minus mu x cube by sigma x cube will be equals to what? Can you calculate and tell me? And also kurtosis ck will be equals to e of x minus mu x to the power 4 by sigma x to the power 4. Tell me these two values.
Minus 2, sir. Skewness.
Minus 2 or plus 2?
Wait, sir. Let me check again.
Yeah, check it because morning I calculate my notebook. Somehow plus 2 I receive. Anybody has calculated anything?
So the skewness is 2.
Plus 2, right?
Yes, sir. Plus
Yeah. Jafar, can you check and tell me? And kurtosis?
sir, kurtosis is 3 by 8.
9. You check again.
Yes, sir. Kurtosis is 9.
9.
Yes, sir, 9.
So, so you see, this is plus 2. Plus 2 means how it will look like. It will be skewed towards right. So if you see this distribution, which is b e to the power minus bx ux, that means from 0 to x it will be. So at 0 it will be b, it will be 0. You see it is this is fx and this is 9. Fine, no issue. So is it okay? Central movement. Others, you can you calculate, right?
Hello, am I audible, sir?
Yes.
Sir,
Tell me.
is there any physical significance of this skewness, like when it is the tail is towards right or when the tail is towards left?
Yeah, this is positive and negative is the significance. Okay. So skewness, that's what I said, that if it is 0, then it is symmetrical. If it is positive, that means it has tail on the right hand side. If it is negative, it is tail on the left hand side. Okay, that means skewed towards right hand side. That means more tail towards right hand side. If it is negative, that means it's more tail towards left hand side or skewed towards. That is the physical interpretation. Okay.
Okay, sir.
Okay. Priya and Shreya, is it fine or you have some problem to follow?
No, sir, it is okay.
Yes, sir. Okay.
Okay. Fine. Kirti, it is also fine to you? Kirti, are you there or it is dropped? Kirti is not there, maybe 1.3.4. Now we move to next section or subsection 1.3.5. So 1.3.5. This is conditional. Always we'll do the conditional because that's what I said, it is very important. Conditional expected values or conditional moments. Let me see if anybody is not there. 7, 8, 9. So conditional expect. So how do you define a conditional expectation? Very simple. Earlier we were saying condition expectation of variable x is e of x. Now we said condition x given a. That means we need to have integration minus infinity plus infinity of x. We must have, instead of PDF, we have the PDF f of x given a small x dx. This is what is the conditional expectation. For discrete random variable, we can write e of x given a will be equals to sum x k, sum over k, probability of x given a small x k. Okay, this is the discrete random variable. Now for any function, so conditional expectation of a function, similarly you could write, so conditional expectation, so e of x, so conditional expectation of a function of conditional of the event, conditional event a, we could write similar way, E of gx given A will be equals to minus infinity to plus infinity gx f of x given A x dx. We could write for discrete E of gx given A will be equals to summation over k gxk p xk. Fine? Understood? So suppose a Gaussian random variable x, we know Gaussian random variable will be equals to 1 by root 2 pi e to the power minus x square by 2, and say a event A, an event that the random variable x is positive, so A equals to x greater than equals to 0. Okay, greater than 0. So then calculate E x given A. Okay, of given x greater solution. Tell me. Quickly do it. Are you doing? Please respond. I could not see you.
Yes, sir, doing.
Do it.
Sir, is it square root 2 divided by pi?
Yeah. So who? Joyce?
Yes, sir.
Okay. So can you say that how you proceed?
Uh, Sir, like I just applied the formula, and for the conditional PDF, it was like fx divided by 0.5.
Yes. So, so to all of you, you see here the important thing is to find out the conditional PDF, right? So that is the most important thing, how to determine the conditional PDF. Once it is done, you can directly do x into conditional PDF dx, right? So how to find out the conditional PDF? That means what will be f of x given a? That is the most important thing to decide. So for that, derive a formula which is very important about the conditional. That formula we said f of x given another event which is in between x to b, and I must keep the bracket, x will be equals to fx of x by probability of a in between x to b. So for a x b and 0 otherwise, right? Everybody recall this formula? This is the important formula.
Yes, sir.
So now if we recall this formula, that means we are saying that here event is x greater than 0. That means the conditional probability when x is less than 0 will not get anything, so it will be 0. And then what will be when it is greater than 0? So it will be, let's discuss, calculate it. So f of x given a means x greater than 0 of small x, it means f of x first we will write directly, that is 1 by root 2 pi e to the power minus x square by 2. And what is the probability of x greater than 0? Definitely it is half, because half part of the Gaussian distribution, so it is half. So if we do such thing, what we will get the conditional probability? That will be 1 by root 2 pi, 1 by 2 will go up, that means root 2 by pi e to the power minus x square by 2, right? So now if you want to calculate the expectation e of x given x greater than 0, means integration from where to where, you can do minus infinity to plus infinity, fine. This I should write, this is for x is we are taking what greater than 0, for x is greater than 0 and otherwise equals to 0 otherwise. Okay, so if you want to do integration, we have to do 0 to infinity, because minus infinity to 0 it will be 0. We need to write x and then fx given this, fx given x greater than 0 small x dx. That means it will be 0 to infinity x root 2 by pi, okay, minus x square by 2 dx. That means it will be root 2 by pi, root 2 by pi integration 0 to infinity x to the power minus x square by 2 dx, right? That means we can take x square as z or y something, then x will cancel out. So we'll get ultimately, or we can do it by partial fraction. Partial fraction is better. It is minus x square by 2 into x. X will be ddx will be 1. 2 by pi root pi to the power minus x square by 2, whose limit will be 0 to infinity. If we put infinity, it will be minus 0. So if you put 0, it will be minus 1. Some problem is there. Minus. So 2 minus 1 root 2 by pi. Is it to all of you? Tell me if it is okay.
Yes, sir.
Okay. Others?
Yes, sir.
Yes, sir.
Okay. Okay. So you see, that earlier what PDF, our Gaussian PDF was here the mean is 0, so it will be like this, right? So when we make so 0 and then e to the power minus x squared by 2, then it will be more peak kind of thing and will go like this, right? So it one-sided, and then we do expectation on it. So this is the thing actually. So whenever you see conditional PDF, so which range this event you say vanish because already that has happened. Okay. Think like this. Okay, now next section will move. This is a very important section. Very, very important section. 1.3.6. Transformation of random variable. This is a very important section. Transformation of random variable. We did not read earlier. Class 10 plus 2. Try to read it. See it. So what we are going to do? Let me as easier as possible. So suppose we have a random variable. We have random x. Okay. We have its CDF. Important as I said, fx of. We have its PDF of. Fx of small x. Now we transform this random variable to y. Okay, y is another random variable. G. That means our y will be equals to now g of x, and here x will be equals to g inverse of y. Now the question is, what will be fy? What will be small fy PDF? So what will be CDF and what will be PDF? This is our now question is. So now try to understand this. Suppose we have a random variable x and we transform this random variable to another random variable by a function g of x. Now if it's earlier PDF is fx, then it will be fy. How these two PDFs will be related? Okay, so this is very important and very frequently come into engineering application, because suppose we have a system. Let's say we have a system and system transfer function. That means if something comes, we'll get something out. Okay, so now if the system, so system is basically a kind of transformation where input goes and there is a function to get output. Now that let's say a random variable comes into the system, goes as y, system function. Mostly PDF, let's see. We are more familiar. So and PDF, which PDF will be look like. So if we know the input of a stochastic input or a random variable, for the time being, let's don't say stochastic, a random variable as input, and we random every moment whenever we do experiment, but the characteristics is not changing. Characteristics means random variable characteristics means it PDF, all those things is not changing. What will be the transform That is now our question. We are going to answer. So as you see in your engineering application as well as many other applications, this is become very important question, because suppose you have a system which is a linear. So we always talk about linear system for the time being, although nonlinear system is more important, because in reality no system as such, no system is linear, or we can say that very less number of systems are linear. So if it is a non-linear system, so then how this input will got change, or how this random numbers will got change, how this PDF will got change. So that is the we are trying. I will to do maybe homework which will be useful for all of you to in your concept or to judge your concept. Now suppose I'm coming this problem. Let's first try to discuss some homework. Suppose you have a your random variable follows a distribution. Okay. Let's say X follows a distribution of normal distribution of zero mean or unity variance. Now if I ask you, you generate 1,000 such random variable. Okay, generate such random variable which follows the distribution of Gaussian from 0 to 1. Okay, other things are also applicable. I can ask you generate 10,000 random variables which follow a uniform distribution. For the timing, I am asking now generate 1,000 such random variables which follows a distribution. So you need to write a code, and you need to know how to generate a random number, and this process is not very easy. So this is your homework. So where you will get reference, you will get reference. So in MATLAB there is a single command. In Python, single command, something you write the syntax, you will get the 1,000 number. That I am not interested. I just want to go deep into the command, that how you can write a code in any language without using any inbuilt subfunction to generate 1,000 such random numbers from this distribution. Okay, so for that what I refer, I don't, the literature has changed. So there are books which we call the numerical recipes, big books we used to read, numerical recipes in C, numerical recipes in numerical recipes. So those books they discuss, so those are available free in internet, and they discuss many algorithms. Among such many, one is how to generate random number. So you can see it, you can read it in any language, even in MATLAB, but without qualification, write your own code and generate the random number. Okay, so I'm giving some basic insight. Suppose if I say that I need to generate a random number of Gaussian distribution such. So if I bucket it, say 0.01 or next bucket or something, and according to the probability we know how much will be. So if this many number we need to generate, we should generate this many number from this probability, we should generate this many number from this bucket, like this. But the algorithm is not so easy, it's just to think about it. So this is your homework. So generation of random number. Next homework will be, so test the generated number follow Gaussian distribution. kind of thing. Suppose I gave you 100 numbers. So I ask you, could you check this number and tell me whether this number follows the Gaussian distribution? How do you do it? Okay. So there are some tests you can do it to check whether the Gaussianity test is there, chi-square test and all. So you can test and tell me, okay, whatever now this is following the Gaussian distribution with this much confidence. Okay, so these two things you do on your homework. These two homeworks. Any comments? I'm coming this transformation. Why this is important? Why this is important? Because you have sufficient number of population, say 1,000, 10,000, or even 1 lakhs. Then you can transform each random variable with the computer G, which you know, and you will get the population of Y. Called it cloud. So if you have cloud of X, you can use the random, we can use the function so that you will get the, then you can use cloud of Y maybe very crudely to just histogram and see how the PDF is looking like, and you can check by your calculation that what like same. Okay, so this way of doing and doing experiment, doing manipulation with them is called the Monte Carlo simulation. Okay, so this is called the Monte Carlo simulation, MC, Monte Carlo simulation. This is very important in any statistical experiment and in developing algorithms. Okay, now tell me, I want to hear your voice. I am not disconnected, right? And speaking.
Yes, sir.
Okay, so you do understand, right, what is you need to do?
Yes, sir.
Or any clarification you want, you can ask now. Anybody?
So please clarify about the question number 1, like what we have to basically do in that question.
So question number 1, is it fine?
So question 2 is fine. Question number 1 I'm asking.
Oh, suppose I tell you, I give me 1,000 number which follow. Is it now clear?
Sir, actually your voice is breaking, so it's not pretty clear about the.
Breaking.
So please explain.
Okay. So what I'm saying, you give me, or you give me 1,000 random number which follows a uniform, sorry, which follows a Gaussian distribution of zero mean and unity variance. Is it now clear?
Okay, sir.
That you have to do. Without using any inbuilt subfunction. Yes, please tell me.
So basically, sir, we have to try it by using MATLAB.
No, MATLAB you can do, but MATLAB there is an inbuilt subfunction. Okay, rand norm, or cannot use that.
Okay, sir.
To write your own code, okay, use MATLAB as a programming language, and you generate the number, but you cannot use this subfunction.
Okay, sir.
If you use the subfunction, there no point. I mean, anybody can do, and it's kind of learning syntax only. This is not useful. It will be useful when you know how to generate, then subroutine and all. Okay, somebody was asking something. Somebody was asking something. If not, so everybody understood, right? What you need to do in homework?
Yes, sir.
Okay.
Yes, sir.
Okay. So this is a very good homework. We'll see with the help of computer, and particularly it is called Monte Carlo simulation. And I will tell you, function will skew this PDF. We are coming basically. I am to come back to the point what I was discussing, that we have a random variable, we have a function variable x to y. We know the random variable x, its PDF. Our question. So to start with, we assume first increasing case 1, case A, G of this is a monotonically increasing monotonic function. Let's assume that first. So we can just draw a little bit. We have random variable x, we have a random variable y, and g is any monotonically increasing function, which is g. So if you have any point small x, this is g, and we project it here, we got small y, which is equals to g of x, right? So this is the thing. So we have monotonically increasing function. So now for this type of increasing function, we have all one-to-one relation. If we have one x here, we have a definitely y for that, and there is no 1-to-2 relation or anything. We have one-to-one relation. So one-to-one relation between one-to-one relation between x and y. So now we can write that y right. Now let us think what will be the CDF or PDF of y. So first let us try to calculate the CDF. So what will be CDF of y? F of y small y will be equals to probability of y having less than equals to small y. So probability of y having less than equals to small y. So it has a one-to-one relation. That means if I want to say that probability of y less than small y, means that this part has the probability of gx. So let's write this way. So f of y, probability of y less than y, that we could write, or here only we could write, that will be equals to probability of y means what? Right. Probability of x take inverse less than equals to g inverse y, or if x is less than equals to g inverse y, that means fx of inverse y. So you see how we are writing fy. So sorry. So what formula we got? F equals okay. That means if we know fx, we know g, so g inverse y, and that will be y. Okay. So now this is a very important formula. Now to get the small fx, we make derivative of it. Okay. So how do you get? So f of y, capital Y, of small y will be equals to dy of fy of y will be equals to fx of g inverse 1 g inverse y will be equals to ddx. We can do that, means fx of g inverse y and dg inverse by dy. Okay, so that means will be equals to g inverse y means what? So y equals to gx. So g inverse y is x, so fx small x, g inverse y is x, dx by dy, x equals to g inverse y. This is the formula. Okay, so how do you get y capital? If y of small y will be equals to x of small x dx by dy equals to g inverse y. Okay, and this could be, it is same, but let's write it. Some book is writing ddx of dy by dx at x equals to g inverse y. Okay, so tell me, everybody agrees to this derivation? This is also very important relation. This is one
Sir,
important relation. Yes.
sir, do we have to take a modulus of dx by dy, because we have a PDF should be positive, so
Yes.
like
PDF should be positive, and here you see dx dy is positive. You are very intelligent. You are telling the correct thing. This should be positive, and that's what we calculate. We took that it is a monotonically increasing function. That's why dy dx is positive.
okay sir,
Do you get it right?
okay sir,
Yeah. And then will come monotonically decreasing. Then you will get minus, so that it becomes positive. Okay. We'll discuss that. This is a good question. Anybody wants to ask any question? Okay, now another important example I'll give. That is also very important example that I'll give. So everybody understand, right, the derivation? So example, let's say our x is a Gaussian random variable, with mean mu, and so we write it like this, with n means Gaussian random variable or normal distribution, with mu and variance is sigma square. Okay, now this is the x. Now our y is ax plus b. What does it mean? It's a linear transformation. It's a linear transformation. Means it is coming to a linear system. It's coming to a linear system. A is greater than 0. So we see that it is a also monotonically increasing function. Now the question is, we know x is a random variable of this. What will be? So we know the fx. Okay, so what will be? What will be? Can you calculate this? So implication is we have a kind of linear relationship and a Gaussian random variable is coming to that. What will be the output? Okay, so it's using formula, it's a very simple. If we use formula f of y, as it is a linear monotonically increasing, f of y will be equals to f of x, this one, f of x small x dx by, means what is f of x? F of x dx dy. So x is what? X equals to it is a mu, so 1 by root 2 pi sigma square, 1 by 1 by root 2 pi sigma square, 1 by root 2 pi sigma square e to the power x minus mu square by 2 sigma square. This is one. So if we do dx by dy, what we'll get? So this will be dx by dy, that means this one. So dy dx by dy dx by dy will be equals to, so y will be equals to ax plus b. Let's do all. So x will be equals to 1 minus b by a. So dx by dy will be equals to 1 by a. So we'll get 1 by a into fx x. So x means what? X minus b by a. So now what is fx of this? To 1 by root 2 pi sigma square and then exponential. Now this is our variable, so it will be y minus b by a minus mu whole square divided by 2 sigma square. So we could write 1 by a 2 sigma square so a into 2 pi sigma square, CL minus is there, a is there, a will come below, minus b minus by 2a sigma square. It means 1 by a root 2 pi sigma square exponential minus y minus b plus a mu whole square by 2a sigma square. A square, maybe A square it will be. A square. So we could write it. We can go inside. Okay, then what we are getting? We are getting it is another random variable of mu and standard deviation a square sigma square. Okay, so all of you could follow this. Just I'm asking. Then I'll give little bit physical interpretation. All of you could follow this. Tell me.
Yes, sir.
Joyce Mridul, is it fine?
Yes, sir. Yes, sir.
Okay. Asna. Asna. Now, what we get, what is the physical interpretation? So we give one Gaussian variable to a linear transformation, and then output you see we get another random variable. Although its mean has been changed, the mean was earlier mu, and the mean now becomes b plus a mu, and its standard deviation is also changed. Earlier it was variance, earlier square, now it becomes a square sigma square. But the point need to carry Gaussian random variables comes to a system, comes to a transformation which is a linear x plus b. X, call it linear loosely. If you go to signal system, then you will say no, it is not linear, this that, but loosely let's take it as linear. So it will remain random variable, but if it is not linear, it will not remain. That will come in the next classes. Okay, so x is Gaussian, y remains still Gaussian, but its mean change, its variance change, but it still remains Gaussian. Okay, is it fine to all of you? So this transformation is very important thing. We will slowly cover this. So, but you see that for a monotonically increasing function, if it is a linear, we give the Gaussian distribution. This is a very useful interpretation. So whenever we'll see that how the Gaussian random variable behaves. Okay, so here you just take it that if any Gaussian random variable comes transformation which is linear, it remains Gaussian, although its mean changes, its spread changes, but still it remains Gaussian, and that is the very beautiful properties. Okay.